So I'd like to thank Avinash and the other organizers for inviting me here. I've spoken at some other IITs, IIT Bhubaneswar, but never at IIT Bombay. So it's great to be here. So I've been working at IBM Research for a long time, and you'd wonder why I do polynomial optimization at IBM. So we have a mathematical sciences department. For a very long time, we even shared some space with Columbia University 70 years ago. But in any case, so some of these things arose from problems that we were trying to solve while at IBM. So a lot of the collaborators, so this is joint work with a lot of different people. As I go through the different parts of the talk, I'll mention the collaborators. So I'll start out talking about what's called symbolic regression, then how to combine, then combining reasoning and regression, and how we try to model this stuff using polynomial optimization, and then also some ideas on improving polynomial optimization, existing. So along the way, I'll also talk about existing approaches to solving polynomial optimization problems. So let me start off with the motivation for the initial work. Suppose, let's start off with the simplest possible regression type problem where you have some data to x-axis, y-axis. You have some data points. You're trying to plot a function, fit a function. Except you want something which is scientifically meaningful, where the scientifically meaningful depends on the context. So in this particular case, we use some of our own code to get some functions, and a bunch of functions like this function, for example, goes off to infinity at 1. So it's something divided by x minus 1. It fits the data beautifully in all these points, but here it goes off to infinity. But we know in this particular context, we're trying to model some physical process. Things should not go off to infinity. So there's a limit. So you want something smooth, and then you want something else to happen at x equals 0. So many of these functions here, things going off to infinity, 3 of these functions are not meaningful, even though they fit the data really well. And how do you distinguish between different functions which fit the data beautifully? It's not really a well-solved problem. Even in 2 dimensions, I really cannot answer this question. Unless I take into account the particular physical context or the scientific context where I'm trying to fit functions. So what the initial part of the talk will be about is what some people call derivable scientific discovery. You're trying to discover formulas, and you're also coming up with a derivation for the formula. So you want to not only come up with a formula, but a derivation or a proof that the formula is accurate. So there's a huge amount of work nowadays in the scientific literature, journals like Nature, etc. You'll find lots of papers on using neural networks to find patterns and relationships. Problem is you get black box relationships. You get a function encoded by a neural network, and it's hard to understand what the function is, even though you can plug in values and get output values. If you do standard regression, that's also widely used. One issue is that you assume a functional form, and the discovery of fitting is really just choosing the parameters. And then widely used approach is what's called symbolic regression, where the functional form is not given, but it's assumed to be something that can be composed from the data and certain input operators. And I'll define this more precisely in a second. So linear regression, symbolic regression, let's say you have data, so bold face x1 to xk, these are data points, and the components are lowercase x1 to xn, and for each data point you have a value y, so capital Y, and you try to find a function, except you're given maybe a list of input operators. You said, take any function with a certain number of symbols that can be composed of a list of input operators. Now, of course, if I just give you plus, minus, multiplication, that's already all possible polynomials. If I add division, you get ratios of polynomials and other complicated, and other functions. So it's already becomes pretty complicated, except there's still a huge body of work on symbolic regression in the computer science literature. Starting in the 70s, a lot of progress from the work of Dexter Koza, and there's a well-known software, Eureka, which implements genetic programming. It's a commercial package. You'd have to pay to buy it. There's some work where I got interested is there's some work we did, and it was done before us by a student of Nick Ioannidis at CMU. So using discrete optimization. My background is mainly discrete optimization, so my interest in this was, can I do something interesting using discrete optimization ideas? And so we came up with some mixed integer nonlinear programming approaches to solve symbolic regression problems. And there's some other recent methods by Udrescu and Tegmark, and there are many different approaches in this area. So let's just get into, spend a minute or two talking about symbolic regression. So one basic idea here is that if you represent the function using an expression tree, let's say, you're trying to find a formula and you represent, so in this particular formula, and it's sort of intuitive what's happening. You take a parent there's an operator, the children, you take the two operators, in this case, two variables, take the product, and then you take this formula which for this node, and then you repeat as you go up the tree. So you can represent an expression in an expression tree, and so searching for formulas is the same as searching for expression trees. Now, how do you do that? In as I said, the most widely used approach in this area is genetic programming. What do people do in this area when they use genetic programming? They basically take a bunch of initial input expression trees, and then they do certain operations. So for example, in this particular picture, so they'll just take each subtree represents a valid expression. So you take the subtrees, you take two subtrees and just swap it. And then you test how well each of the new expressions fits the data, and you just repeat thousands of times, and quite shockingly, they actually get reasonable answers every so often. And it's not just for scientific formulas. You can even learn programs, and people have used genetic programming. If you start thinking of nodes as not just plus minus, but if, then, else, and operators, you can learn programs this way. So one big issue in genetic programming based approaches is that you can't really control the size of the tree. So what then they do is they add an additional penalty in the objective. Besides the quality of the fit to the data, they'll also add a penalty, maybe the number of nodes in the tree. They penalize that and then try to use that to reduce what they call bloat, the size of the tree. And that's still fairly successful. So some of the earlier mixed integer nonlinear programming formulations, they basically try to have variables to learn these expression trees. So let's say you fix a depth. You said depth 3 or 4 or 5. You'll have a variable deciding what operator will go in each node. Variables deciding what, so here it's tricky when I'm using the word variable. The variables of the problem and the variables of your optimization formulation. So the variables in the optimization formulation deciding which variables go in the leaf nodes, which operators go in the non-leaf nodes, and then additional variables, continuous variables, which will try to compute the effect of the tree on the data. Becomes pretty complicated, so it becomes, that's why it's mixed integer and nonlinear. So what we did a piece of work recently, created a software called AI Descartes, where we basically do this symbolic regression to learn formulas, but then we were trying to go beyond just regression. As I said, if you don't use some background information, you really cannot distinguish between formulas. So what we do is we try to combine background theory in a specific way in this first piece of work, which is the motivation for the later polynomial work. And so what we do is we use symbolic regression to learn a bunch of formulas, and maybe use even mixed integer nonlinear programming in the process, and I'll talk a little bit more about that. And then later on try to use background theory to distinguish between the formulas. So if you have 10 different formulas, we'll try to decide which ones are more consistent with background theory, which ones are less. And I'll describe that process in a second. So first thing we decided is that we had to change the mixed integer nonlinear programming formulations because those are very difficult to solve beyond a certain size. The biggest problem in these areas, and so for those who work in discrete optimization, a huge issue is whenever I can take a collection of variables, I can swap the values, I can permute the values and still get another feasible solution. That typically makes a problem hard to solve in integer programming. And that's a problem in expression trees. If I take these two variables, if I have an operator like this, multiplication, I flip here, there was x and y, I make it y and x, I still get the same expression tree. And then, so those correspond to different solutions of your optimization formulation, adds difficulty. So what we try to do is we try to come up with a different formulation, what we called So to try to reduce some level of symmetry, we, instead of working with single variables, problem variables in each node, we called each node we defined as a like a what we call a Laurent monomial. This Laurent polynomial, you have Laurent monomial, so you have a constant times a power of a variable, and the power could be positive or negative. So in this case, all positive powers, this case negative powers, and the powers are what we are learning. So we're assuming every child node has all variables in the problem, but what are the decision variables are the positive and negative powers. And then we do some additional heuristic idea. So it's not a true optimization formulation in the sense that you're not guaranteed to get an optimal solution, but we do certain other things to remove symmetry. For example, if there was a division, L1 divided by L2 is also representable as a single Laurent monomial. So we get rid of possible trees which could lead to symmetric solutions. So I won't get into the details of this formulation. Suffice to say that it's not very, we not only define a formulation, we define a solution approach based on some level of combination of enumeration. In particular, we try to avoid some level of nonlinearity by avoiding variables for the choices of the operators here. Instead, we do some level of enumeration. So fix the operators, but keep the powers of the variables to be unknown. And then fix the depth of the trees. And doing that, we're able to get better solutions than some of the competing codes. So these are the sort of formulas we're trying to learn from data. So there's a list, a nice paper, AI Feynman. They took 100 problems from the Feynman lecture notes and created data. So they have a synthetic data set. So what we're trying to do is we're trying to learn these formulas from the data using symbolic regression. As you can see, they start getting complicated. You will have square roots, squares, plus, minus. These will be the input operators, and you're trying to see how you combine them. And once you have noise, it's very hard to recover this. So even simple ones, what you think looks very simple, let's say this one. So there are a lot of competing codes which could not obtain it beware, but we could also obtain some other simple functions. For example, this function, with a little bit of noise, we could not, none of the competing codes could, including ours, could not recover this formula. So in any case, the point is that we're able to improve over the state of the art in symbolic regression, get a slightly larger number of formulas out of, let's say, 81, which you could handle, given the list of operators. We were using a mixed integer nonlinear programming solver Baron. So that cannot handle trigonometric functions, but it can handle exponentials. So that's why we allowed those problems, 81 problems which involve sort of addition, subtraction, multiplication, but also exponentiation and logarithms, but no trigonometric functions. So there's still a lot to be desired. So we can still get only 60 odd. So when I say we can get these functions, what I mean is that it's not that we know upfront that this is the correct function. We're just saying among the functions we can recover, is one of our candidate formulas one of these formulas? And if so, we declare success. That's only 60% for our code and less for other codes. But once we do that, how do we combine background information? And that I'll sort of mention a little bit and then talk about how we generalize to polynomials. So there are many different ways you can take background information in and use it. So some standard things you could do is you could say, you could test for monotonicity. Is your function non-decreasing? Is your function, you can try to take the conditions of the limit. Is it non-negative over the entire plane or Euclidean space? So these are constraints which are somewhat straightforward and not necessarily easy to check, but at least they're explicitly defined and you can check the function depending on the function. Of course, if it's a neural network, you don't know, you can't check these. You need an explicit function for some of these to be able to check them. And then the second type of reasoning we want to do is derivability. If you have a list of axioms in a background theory, you want to check if a formula can actually follow from the axioms. For this, we use a theorem prover called Chimera X. So we'd actually give a list of axioms and say, is this formula, does it follow from a list of axioms? But the more interesting use of a theorem prover is when we said, okay, suppose we cannot verify that a formula follows from the background theory, but is it close to another formula which follows from the background theory? And so we defined distance to derivability. And the way to think about it is there's a family of functions which can be derived with axioms, and you're trying to see how close are you to the family of functions, where you define a distance between pair of functions. So let's give a simple example here. So this is Kepler's third law of planetary motion. The period P is a function of the masses of two objects, let's say a planet and the sun. There's a gravitational constant, and D is a distance to the between the two planets. So you can define, so firstly Kepler found this without Newton's laws. It preceded Newton's laws. But suppose you knew Newton's laws of motion and his laws of gravitation, you could write down a bunch of axioms in a bunch of variables and then try to derive Kepler's third law. But here's an interesting point. You'll end up having, when you write down such a set of expressions, you'll have variables which are not really measured. So what is common in Kepler's law, or even in current planetary observations, you can measure, you can estimate distances, you can estimate periods. Masses are a little bit more complicated, but let's say you can do that. What you can't really do is you can't calculate forces, you can't calculate some other things. So there are variables in this background theory which are not present in your measured data. So you have data, you have additional variables which are not measured. So you have to somehow derive from this, you would like to derive from this list of axioms whether or not that particular formula follows. So let's see what sort of results we could get. When you actually start using real life data, there are all sorts of issues which show up, and then I won't get into all of them, but I'll mention a few. But let's say you're looking at the solar system. So solar system, first thing is that if you look at this formula, you notice that M1 and M2 in the solar system, M1 is, let's say, the mass of the sun, that's constant. Once it's constant, there's no real way you can, no easy way to really find this formula when one of the variables is a constant. And that's exactly what will happen in here, symbolic regression packages. So it might show up with this function where, and the masses of the planets are too small relative to the sun. So given that all these things have some numerical error and numerical precision, the masses don't even show up. So these are formulas we'll get only involving D. Well, but even then, can you say anything about this if you had the background theory? So first thing, you get some numerical error, and you'd say, okay, this is probably the best for the solar system data in terms of numerical error. It turns out that the background theory, using this notion of distance to derivability, would be able to say, yes, in fact, this is the best out of these three functions. Now you go to NASA's now, you can find on NASA's website exoplanet data, data about planetary systems outside the solar system. When we use now, you have different solar masses. So we took data from two or three different solar systems. So now the M1, the mass of the sun, is varying. So now that pops up in the symbolic regression packages. Again, here the nicest one, which would naturally follow from Kepler's third law, happened to be both least numerical error and least, we define a notion, distance to derivability in a certain way. Let's not worry about the different columns, but I'll point out one more. But when we take data for binary stars, so two stars rotating around a common center of gravity, here the formulas we found with least numerical error were actually least consistent, were not very well consistent with the background theory. Using our Chimera solver, so we were able to verify that the one which is closest to Kepler's, so this closest, if I replace this by 1, this is actually Kepler's law subject to a constant. So if I measure in the appropriate units, you can get rid of the 4 pi square and the g. And so the formula I'm showing down here is exactly Kepler's third law. So this would pop out. This has higher numerical error than these other formulas, but closest to the background theory in terms of distance to derivability. So that adding the distance to derivability allowed us to then isolate this formula as, in some sense, the nicest formula, most consistent with the background theory. I'll give you another example here. This is Langmuir's adsorption equation. It basically talks, it's a very simple formula. So Q is, let's say you're trying to measure Q as a function of P. The rest are constants. You're basically saying you have a surface, metallic surface. You're trying to, with some holes on the surface, you're trying to pass some gas like carbon dioxide. You're trying to see, is the gas sticking between the holes in the metals? And as you put higher pressure, more and more gas sticks to the surface. And this is really a function of amount of gas sticking to a surface subject to pressure on the x-axis, amount of gas sticking on the y-axis. And this is what I was saying, because it's amount of gas, when there's no pressure, no gas sticks, you assume that the function has to be zero. As you start approaching infinite pressure, it flattens out. So you can assume from first principles that certain basic things will hold. You can come up with some basic properties of what your function should look like. But you can also, what Langmuir did is also came up with some background theory explaining how these, in terms of notions which are not really measurable, as in these S, really these variables S represent how many holes you have on the surface. Of course, you're not counting how many intermolecular gaps you have on the surface. So these are things you cannot measure, all these S's. However, in the background theory, when we tell the theorem prover, so here I'll give some, show the types of functions we get when you use symbolic regression packages, and lots of different functions of the same type, even if you stick to simple polynomials or ratios of polynomials, and these are the plots. And this is the first plot I showed earlier, a lot of things going off to infinity and scientifically less meaningful. However, some of them we're able to derive with Chimera and show that these are consistent with the background theory, and some others not. So this motivated some of our work on subsequent work with polynomials. We observed that a lot of the polynomials we're looking at, say even Langmuir's function here, Kepler's third law. Kepler's third law is obviously not a polynomial. However, if you square left hand side and right hand side, move things around, you can write the whole thing as one polynomial expression equal to 0. And so, and that's true in a lot of physics examples and Feynman's lectures. A lot of the problems can be expressed as the formulas can be written as sums of ratios of polynomials. And so if you also assume that the background knowledge can be expressed in terms of polynomial equations and inequalities, then you can start bringing in a lot of well-developed literature on polynomial optimization, because learning formulas that are rational polynomial expressions can be reformulated in terms of polynomial optimization. So some of these ideas were already there in a paper by Bashir El-Khadir and Amir Ali Amiri, and Bashir collaborated with us on this current paper, which we just published a couple of months ago. So let me now get into a few sort of a quick digression into polynomial optimization, and then I'll get back into how we use that in this context. So the most basic ideas in polynomial optimization are as follows. Let's say you have a bunch of polynomials, say Px, and so these are all polynomials. The P's and Q's on the top of the slide here, these are all polynomials, and let's say we fix n variables, so multivariate polynomials, and the maximum degree of sum of powers in any monomial is d. If Px was a sum of squares of other polynomials, of course each of these squares is non-negative, the sum is non-negative, so P of x is non-negative for all x in the Euclidean space. Hilbert showed a very nice sort of converse result, saying that if P of x is univariate or quadratic, quadratic means you have products, multivariate quadratic, so pairs of variables are multiplied together, or the specific combination of number of variables and the degree is this much, so 2 variables at most degree 4, so you have finite number of monomials. In each of these cases, if P of x was non-negative on the entire Euclidean space, then P of x is a sum of squares of simpler polynomials. So this and in every other case, he showed that there would be instances where P of x would be non-negative but not a sum of squares. So by the way, if P of x has this decomposition, I'll call it an SOS polynomial or sum of squares polynomial. So now, what is that to do with optimization? Well, if I want to just minimize P of x subject to x and Rn, I can rewrite it as max of lambda such that Px minus lambda is non-negative. And that can be replaced, I can replace this condition using these ideas of sum of squares, I can replace it by this condition. So this would be relaxation, and this would get a lower bound on this true optimal value. And furthermore, this problem can be reformulated as a semi-definite optimization problem. And this is the most basic idea in polynomial optimization. Of course, they do a lot more. So before I go ahead into constraint polynomial, let me get into what additional work they do there. So here's an explicit example of a polynomial in two variables, which is non-negative, but not a sum of squares. And you can prove that this is non-negative using the AMGM inequality, arithmetic geometric mean. You take these three guys, the sum of these three is greater than the product of these three cube root. So you take the product of these three, you get x6, y6. So 3 times the product of these cube root, and which is exactly this term. So this sum is greater than this sum, this term, and that's why this whole thing is non-negative. But Artin showed a beautiful result saying that if p of x is, if polynomial is non-negative, this is from the 1920s, if polynomial is non-negative, then it is a sum of ratios of polynomials squared. Not sum of polynomials squared, but a sum of ratios of polynomials squared, which can be rewritten as if p of x is non-negative, then there's some polynomial q of x, such that p of x times q of x squared equals a sum of squares. And this is in fact a proof for and this is a specific application of Artin's idea to the Motzkin polynomial. Motzkin polynomial, this polynomial times x squared plus y squared squared is equal to the specific sum of squares. And the basic idea in polynomial optimization is just as when we talked about replacing non-negative by sum of squares. Now when you want to do Artin's idea, you want to show something is non-negative. Instead of just showing that p of x minus lambda is sum of squares, you try to show p of x minus lambda times a polynomial, an unknown polynomial, is a sum of squares. And that's the basic idea. A huge problem in this approach is that the difficulty blows up very fast. Suppose p of x minus lambda is SOS, this bound is too far away from this true value. Then typically you would multiply p of x minus lambda with a certain degree polynomial and then show that that whole product is SOS. And then the sizes of the semi-definite programs are used in these, while doing this, they blow up very fast and then become intractable very quickly. And we had some ideas on that, which I'll talk about briefly later. So that is all about unconstrained polynomial optimization, essentially a summary of unconstrained. Now what happens when you have constrained polynomial optimization? So you have, let's say, a set G, a set of points satisfying a bunch of polynomial inequalities, another set H of real numbers satisfying a bunch of polynomial equations. I should mention up front that this is not actually adding more generality. It's not hard to show that if you're looking at real solutions for polynomial equations, that is essentially equivalent to finding real solutions of polynomial inequalities. They're essentially the same. If you, in one case, if you add some variables to this problem, you get back this problem. Or rather, if you can solve this, well, one way is easy. This seems more general, but they are the same level of generality. Anyway, so coming back, suppose this set G intersection H, suppose the set G rather satisfies something called the Archimedean property. The Archimedean property is something which is stricter, or rather more restrictive than compactness. So if it satisfies the Archimedean property, then you have a very nice result of Putinar, which says that if f of x is non-negative, there is a nice certificate that f of x is non-negative for points satisfying these polynomial inequalities, and it's of this form. It's sum of squares polynomial alpha 0 plus you have multiples alpha ix which multiply the gi's. These are sum of squares polynomials, so these are non-negative, and these are arbitrary polynomials. So if you look at this, if f had this expression, well, this is non-negative. For any point satisfying inside script G, inside capital G, these are non-negative. These are always non-negative for all x. So this product is non-negative, and this is always 0. So this product is 0. So then this whole thing, if you had a certificate, this would show f of x is non-negative on G intersection H. But Putinar's results give some sufficient conditions for such a relationship to exist. So what we do in our work, so after we did the prior work, we started expressing. So I'll jump ahead. So for Kepler's third law, we're trying to find this expression. What we say that, well, if this polynomial is true, And after modifying things, you're squaring the left hand side, right hand side, moving the denominator up, we get a polynomial expression in P. So what we say, if that is true, there should ideally exist some sort of a certificate from all the axioms which we rewrite. Again, if I jump back, these were the axioms. Again, I rewrite all of these as polynomial expressions. So fg d square minus gm1 m2, that's essentially what we're doing in those out here. So we're rewriting the axioms in which we use for Kepler's third law. We're only taking the equations, by the way, dropping all the strict inequalities, we're dropping them. We're just looking at this and saying, well, can we derive from these by, and notice that in this case, we're even dropping the g's. So we just have the h's and we're trying to find multipliers bj, beta j, such that fx equals beta j hj. So hj are all the equations. And we set up a search problem and we search for something which is a consequence of this and actually matches Kepler's third law of the formula. And in fact, it does. So we find out that this formula is equivalent to Kepler's third law. And in fact, we can find certificate, we can find exactly these multipliers, which when multiplied by these axioms, when you multiply by these axioms and add them up, you get this expression, which can be, after rearranging, you'll find that it's equivalent to Kepler's third law. And then we set up an optimization problem. In fact, it turned out to be even a linear optimization problem in this case, because we're avoiding inequalities here. We just have equations, and I won't get into details. But searching for this certificate, so we think of the certificate as these multipliers for each of the axioms. These are unknowns. So what do you mean by a polynomial is unknown? The coefficients of the monomials in the polynomial are unknown. And that's what we're searching for in this case. And in fact, this gives the precise details. So we're searching for a solution polynomial. We have some observations. We're minimizing the solution polynomial values on the observations. And we keep trying different degrees of the certificate. So we say, suppose we look for a degree 5 polynomial using degree 6 certificates, as in these multipliers up to degree 6. Then we get the specific certificate in this polynomial. And we keep increasing degree till we find the right. So with this, so we were able to do this with a number of different problems. It still becomes pretty intractable pretty quickly. The polynomials again grow very quickly. So recently we started looking at trying to use Grosvenor bases. So Grosvenor bases are way to manipulate polynomial equations. So we're trying to discover again Kepler's third law from background theory. From this axioms, we're trying to derive this as a consequence of that. Instead of using polynomial optimization, we're trying to use Grosvenor bases. And one way to think about these polynomial optimization, so what we're trying to do is if you look at the set of solutions, the real valued solutions on this set of variables, it defines what people call a variety. So some sort of a surface in higher dimensional space. And you're now trying to find a surface on a lower dimensional space using only these variables d1, d2, m1, m2, and p. You're trying to, and maybe g, I guess. Anyway, trying to find a surface on a lower dimensional space. And a lot of this idea, so this is just a pictorial description. This is one constraint, fc equals fg, a bunch of other things, and you're trying to project onto a lower dimensional space. And some of these ideas of projection and eliminating variables can be done by first encoding these axioms as an ideal, meaning a set of polynomials and the set of all possible, so the ideal is simply the set of all possible combinations of the polynomials with polynomial multipliers. And the ideal and its variety are connected. And then you're trying to project this down, and this can be done with Grosvenor basis. So Grosvenor basis is a particular way of representing polynomials, just as the way when you have a set of linear expressions, linear expressions on x1 to xn, you do Gaussian elimination, you get the basis, you get a collection of rows which are linearly independent, represent all the equations. Grosvenor basis is a generalization of this idea of Gaussian elimination. You can get a basis representing these polynomials, and then you can do many operations. This projection operation can be done very nicely using Grosvenor basis. There's one subtlety here is that we're interested in real valued solutions. Grosvenor basis, when you talk about varieties and Grosvenor basis, you're looking at real and complex valued solutions. So you're not eliminating any complex solutions when you do Grosvenor basis calculations, but you keep your complex solutions around. There's some subtleties there which I won't get into. So I'll just mention that I won't get into a lot of details in this topic because I want to mention the last topic before I finish. But suffice to say that computing Grosvenor basis is a standard approach in algebraic geometry. You can compute Grosvenor basis and then do the projection in a very nice way using certain results from Grosvenor basis. I'll mention one related problem which we also recently been working on, but it's ongoing work. Suppose you have a collection of axioms and you are trying to derive a formula, but now you want to do a reverse inference. You drop an axiom and you find your formula and you say, can I go back and rediscover my axiom if I had the final formula? And maybe that you have enough data that you can actually recover the final formula from data. Can you go back and recover a missing axiom? Again, it turns out using ideas from algebraic geometry, Grosvenor basis, and one more thing called primary decompositions, you can get back in some situations. Again, we're working on this. It's not complete. This work is not complete. There are again some subtleties. If I have an axiom, one axiom plus another axiom is also a valid axiom. So if you think about a system of linear equations, if I take any equation and add it to another equation, that's also a valid system. So how do I, if I'm trying to rediscover this, how do I rediscover this and not WP minus 1 plus FC minus FG plus this? So you have to somehow tease out the effects of all the other axioms. And for that, you have to use an approach called primary decomposition, so which takes a variety and decomposes it into an intersection of a bunch of other ideals. And I'm not going to get into a lot of details here, but let's say that this can be done. And we are able to successfully do abductive, this is called abductive inference. So we have systems of axioms and for many different problems, Compton scattering, Einstein's time dilation problem, etc. We systematically go drop an axiom and see if you can recover it if you have the final formula. Sometimes you cannot. Most of the examples we looked at, we were able to do so. So the final thing I'll come to, which is trying to improve polynomial optimization, and I won't get into a lot of details, but just give one very high level idea which we recently have started looking at and have some nice results on. So if you recall, we talked about certificates. How do we show that Motzkin's polynomial is non-negative, for example, right? So one thing about Motzkin polynomial is that there was Artin's theorem, which you cannot use Hilbert's ideas and SOS certificates to show that Motzkin was polynomial. So this polynomial was non-negative, but you could show using Artin's result that this is a sum of ratios of polynomials squared. But instead, what we recently started thinking about, motivated by discrete optimization ideas, was to try to partition the space, the Euclidean space, and then to show non-negativity on each part of the space. In particular, by the way, this is just Motzkin's polynomial written with x1, x2 instead of x and y. What we can show is that suppose we have this expression, just focus on this for a second, x1, x2, and we're now partitioning the space in the following way. We're saying x1, x2 is non-negative. So it's this union of these two regions, or negative x1, x2 is, or x1, x2 is non-positive, so union of these two regions. So if I look at the union of these two regions, I can rewrite the Motzkin polynomial in this way as a sum of squares plus x1, x2 time a squared a polynomial. And so when x1, x2 is non-negative, this whole thing becomes non-negative. When x1, x2 is non-positive, this second expression shows that this is non-negative because this is non-positive here and here. So on this white region, this expression shows Motzkin is non-negative. On this shaded region, this shows it's non-negative. So in other words, we partition the entire space into two areas. Now you can do this recursively. And in fact, so the idea would be here that you would start off with, the Euclidean space, and maybe you would come up with some partition, some polynomial expression partitioning the space, and you try to show it's non-negative here, and maybe you succeed, but maybe you do not succeed in this region, then maybe you want to partition it further. So this would be like spatial branching used by Lindroth and many others to solve continuous optimization problems. But except now we're trying to use it in a particular way in polynomial optimization. Question is, are we always, and the nice thing about this approach is we avoid a blow up in the degrees by this recursive partitioning, unlike say in Artin's theorem, which you had to increase the degree of your multipliers and the certificates. Is it always possible to have a low degree certificate of this type? And we have some positive answers. So we're able to first, to do the results, we have to translate everything into the language of homogeneous polynomials. It turns out that you can convert a polynomial into homogeneous polynomial and preserve non-negativity. So homogeneous as in all monomials are the same degrees. So 6, 6 and so on. So homogenization preserves non-negativity. And this is a homogenization of the Motzkin polynomial. And now we have this notion, we formalize a notion we talked about of partitioning the space. We call it an algebraic disjunction. So partitioning the Euclidean space in a bunch of regions, each of which is defined by a bunch of polynomial inequalities. And then we want a certificate. We're talking about sum of squares with respect to an algebraic disjunction. So this is just a generalization of what I wrote down for the Motzkin polynomial. So for every region, I'm writing down sum of squares plus sum of square multiples times the boundaries of the region. And so when these guys are non-negative, this is non-negative, this is always non-negative, this sum is non-negative. So you have a non-negativity certificate, easy non-negativity certificate per region. So what we have is we have a result which says that for any fixed dimension n and even degree, if a polynomial is of odd degree, then they don't have, you can't, they're not non-negative. You can always choose, you can always drive them to negative infinity. So if for any fixed dimension n and any even degree, there exists some family of disjunctions indexed by R such that for any positive, so if I give a strictly positive polynomial, we have a certificate, what we call this SOS certificate, SOS with respect to algebraic disjunction, similar to the certificate we had for Motzkin. We have such a certificate for some one of the disjunctions. And in particular, we have disjunctions, in our theoretical result, we have disjunction defined by spherical caps. So as in these regions we're defining as a sort of similar to circular regions. This is not, let's say, what we would use in a practical situation, but at least it shows that there is a certificate of non-negativity for any polynomial. There are some subtleties here, so I'll be happy to discuss this further. And finally, we did some numerical experiments, some well-known non-negative polynomials which are not SOS, and how many subregions would we need to create before we could have a certificate of non-negativity in each one of them. So in this particular case is a lower bound, number of regions. In this particular case, as you can see, up to 6 regions with a certain lower bound of negative 4.5, 7 subregions we jumped, by 8 we already got 0 as the lower bound and showed that this polynomial was non-negative. And then a different number of regions in each case. Sometimes it took us a little bit more in this case. So to conclude, first in the stuff about learning functions in the scientific discovery context, there are many things we cannot do. No, we do not know. In general, these are open problems. What if the background knowledge has not just polynomial expressions but differential equations? Dx over dt equals something. How do you handle that? We don't know how to do it. What happens if you have trigonometric functions? This is actually closely related to polynomial functions. If I have variables representing cos theta and sin theta, I can artificially introduce the polynomial the equation x squared plus y squared equals 1, and then somehow do stuff. But we don't have we don't have a full understanding of this situation. Much more complicated. How do you handle exponential functions? We don't know that. Coming back to this final polynomial optimization and the disjunctive certificates I talked about, there are many open questions. How do you dynamically partition the Euclidean space to make this whole process efficient? We have some preliminary expressions, but this is essentially saying, how do you do branch and bound? One way of thinking about it is we have defined the notion of a branch and bound to do polynomial optimization, but we just have the most basic initial description and it's completely wide open. How do you efficiently partition the space in a recursive manner? There are many choices one can choose, one can make, and we don't have the good answers for this problem, and it's wide open. So I'd like to stop here and thank you for your time.
So a couple of questions.
Sure, please.
A couple of 100 questions.
Yeah.
A couple of questions to begin with. One.
Go back.
Yeah. So you are using spherical caps. So you're not actually doing it like you're doing a cover rather than a disjunction.
Yes, this is really a cover. Yeah, absolutely.
And So it's interesting. You're actually using sort of convex, like disjunctive sets.
Right. So basically, when I say spherical cap, what one can show is that it's something like if a polynomial is strictly positive at a point, then you can draw a little ball around it and say you can write a certificate whether you can use the boundary of the ball as the disjunction where you're going to yeah, but it's not a satisfying thing. This is not nice. This is enough to show that there exists some family, but it's not nice in terms of actually doing branching.
And maybe just a follow-up question for the experiments actually.
Yeah.
So how did you actually, how did you search was this just regular spatial branching or was it with polynomials?
No, with polynomials, okay. Right, with polynomials. So this one is a little subtle, as in what we did is we came up with this idea of a alternative. Suppose I look at this, let's look at the Motzkin polynomial, that might give an idea. So I'm trying to find a certificate, and I'm trying to find a certificate in two different regions. What do I do is that if suppose up front I had these fixed, but not this one, then I could try to find what is my best choice of my partitioning polynomial so that given these other pieces, it'll give me the best bounds on each side. So what we do is we do an alternating minimization. So we say, okay, we fix some things. And then, so we start off with a random partition. Let's say we start off with a random polynomial partition. So it's actually a polynomial function. For a fixed polynomial, searching for these is a semi-definite optimization problem. But once we find the semi-definite optimization multipliers, we fix them and then go back and say, let me try to modify this guy. So we do that for a few rounds to get a better partition. And once we have fixed that partition, then we take each side and partition further. So that's where the number of regions comes in. But as you can see, that already tells you that even finding the partition, whereas in integer programming, it's very natural, your variables. But again, even there, when you start partitioning over disjunctions, that starts, that's sort of, it's like that. So we're saying maybe if the partitions are on individual variables, if this was just, x1 non-negative, or for various reasons, in this case, we need a even number here, so even power. But because these homogeneous polynomials, various issues, but you could think of that as, I could take very simple monomials as my partitions, but what happens if I do something more complicated? We have no good answers there.
Thanks, Sanjeeb.
Thank you.